Yes? Okay.
Yes.
All right, so I just took those, the results of our ionized swap and crossover and put them up here. So now we have our full equation with a product. So we know that this reaction actually goes, and if we scan through it really quickly, we'll see that we, in fact, already have a balanced equation. So our complete ionic equation is, as always, breaking these down, anything that's aqueous, and however many of them there are. And for each one of these, there's only one. Notice the hydroxide. The hydroxide, we leave it together, that's a polyatomic ion. Our water is a liquid, so we leave it together. And K plus and Br minus because it's aqueous. These are all aqueous too, but I'm not going to worry about them right now because I'm going to get rid of them. So our net ionic equation, we get rid of our spectator ions. Okay, I just can't leave that there. That bothers me. Okay, so spectator ions. The fastest way to figure out spectator ions is to look to see what ions are left on the product side. So K plus, Br minus, Br minus. And our net ionic equation for this strong acid, strong base, and I think you'll remember this if you've looked at the videos, this is always the net ionic equation for a strong acid, strong base neutralization reaction. All right, so that's these two. Now we're going to do a displacement reaction. This is a redox reaction. And we call it displacement because literally the ion in solution is displacing, nope, I got that wrong, because literally the element that's a solid is going to be displacing the ion that's in solution, and the ion is going to become a solid. Okay, so we have our iron, which is a solid, and tin chloride, and this is tin 2 chloride, because remember tin can be more than one, have more than one oxidation state. And we're going to figure out what we have. And remember, for this we need to use our half reactions. So our first half reaction is going to be our oxidation. Now our oxidation is going to be the thing that loses electrons, right? The substance that loses electrons. And iron is going to, the solid, is going to be losing electrons because iron becomes a positive charge, a cation. Now we can choose which one we want here because I didn't specify. So I'm going to make this easy on myself and say iron is going to become iron 2 plus, which is now aqueous, and 2 electrons. And this is my oxidation half reaction. My reduction half reaction then is going to be working with the cation. So I have Sn 2 plus, and that's going to become tin solid. And this is going to be my reduction, which means my electrons are going to be taken in by the tin 2 plus to become tin solid. I'm now going to add these half reactions to get a whole reaction, and I have my electrons canceling out. And I'm going to get solid iron plus tin 2 plus becomes tin solid and iron 2 plus. And that's my net ionic equation. This is a cool one because we get our net ionic equation first. Now for our complete ionic equation, we're going to add back in our spectator ion. All this time, the 2 chlorides have been doing nothing. They've just been sitting there in solution, floating around, while these two play soccer with the electrons. So now we're going to put them back in for our complete ionic equation. And if you're getting a little bit lost, watch the next videos for lecture because we cover this.
Chlorine.
Good thing I have Aaron here to keep me honest. All right, so we've done this one. Now we're going to look at our gas forming reactions. These are the ones that are going to bubble like crazy, and we have two types. We have redox, or a displacement reaction, but in this case you have a metal and an acid, and we have metathesis or ion exchange, in which case you have an acid and a carbonate or a hydrogen carbonate. So really fast, we're going to go through these because you've now seen how to do this, and I've walked you through the net ionic and the complete ionic for both types. So we're going to do this fast. First of all, our zinc solid, we're going to react it with nitric acid. Our zinc, here are our half reactions. The first one is going to be the zinc, which is a solid. In the elementary level of displacement reactions, our solid metal is always going to be oxidized. So that's a big hint. Zinc is going to become zinc 2+. Remember, that's one of the transition metals that only has one charge possible, or one oxidation state. Plus 2 electrons, and this is our oxidation half reaction. So the other thing that's positively charged is H+. So we're going to take our H+, and that's going to be reduced. But when you take H+, when you take any hydrogens, and you form hydrogen, the element, what's special about it? It's a diatomic molecule. It becomes H2 gas. There's no such thing as H, okay? H2 gas. So I've got an issue all of a sudden. All of a sudden, I need to have 2 of those, don't I? Otherwise, my atoms don't balance. And now I have, in order for my charges to balance, I'm going to need 2 electrons. Now to get my complete net ionic equation, I just add my half reactions together. This isn't always this easy. Sometimes you have to adjust the half reactions in order to get equal number of electrons, but I chose 2 that are easy. So our electrons cancel, and we end up with zinc and 2H+, becoming hydrogen gas, and zinc 2+. Now you can see immediately that if I were to write the complete molecular equation, I'd have zinc Cl2. Well, you can't see that yet. Never mind. Hold on. So this is my net ionic equation. You can see right here, that's my product. That's what's going to fizz and bubble. Okay, so now we're going to go to our complete ionic equation by adding back in our spectator ion, which is nitrate. It's just been sitting there as nitrate, it's done nothing else. So we have zinc, solid, plus 2H+. Well, if I have 2H+, I must have to have had 2 there, which means I have 2 nitrates. And for this side of the equation, that way, I'm going to have my H2 gas and my zinc 2+ aqueous and my 2 nitrates. And that is my complete ionic equation. Now I can easily see that I'm going to end up with zinc nitrate and hydrogen gas. Gas forming. All right, our last one. You've been very patient, but this will make your post-lab so much easier. Our last one is going to be nitric acid and acid and a carbonate. Oops, that's a solid. And we don't know what it's going to become. Well, I'm going to do this really fast. H plus, NO3 minus. I'm going to be swapping with Ca2 plus, CO3 2 minus. So I get H plus, CO3 2 minus. I'm swapping again, Ca2 plus, NO3 minus. Cross over H2CO3 and CaNO3 2. Now, I can see you already going for your solubility tables. You've got that as aqueous, super. Uh-oh, carbonates. Well, if you look at your solubility table, it says most carbonates are precipitates. They are not soluble. They're not talking about this. This is an acid. And the thing about this acid, this is carbonic acid, it breaks down very quickly at room temperature and atmospheric pressure to water and carbon dioxide gas. Hey, there's the gas forming. So now I'm going to put this up here, and I'm going to say, oh, wait a minute, I needed 2 hydrogens, and I needed 2 nitrates, so I better put a 2 in here. So my complete molecular equation my complete molecular equation. Let's take this to our complete ionic. You should be getting the hang of this by now. 2H plus 2NO3 minus plus, this is a solid, so we leave that together. CaCO3, solid, becomes water, liquid, we leave that together because it's a product, and so is carbon dioxide, our gas. And finally, we have calcium 2 plus and 2 nitrates. So that's our complete ionic equation. Of course, adding in the aqueous is where you need to. So finally, we want our net ionic equation. Starting over here, I have calcium 2 plus, nope. Okay, we'll try this. Nitrate. Yes, I have a nitrate. So my net ionic equation here is 2H plus calcium carbonate becomes water and carbon dioxide, and I still have an ion over here, calcium 2 plus. And that's my net. Got that in the wrong place. This is my net ionic equation. Okay, so I hope you took notes on that because that's going to help you a tremendous amount doing your post lab. See you in lab.